Hello, everyone. Welcome to MACSMIN2025. Now, Dr. Jonathan McManus will talk about computing the bridge length of periodic point sets. Over to you, Jonathan, please.
Thank you. Hi, so I'm going to sort of go a little bit on the other end of the spectrum from Dan's talk. Very tough to follow. Be the next person on from. Very easy to follow. So this is something that Vitaly briefly hinted at when he was talking about the ISO sets, which are fully complete, but as Dan mentioned, do take a lot longer to compute. And so my work is originally was based on improving that computation time, but I think holds value in itself. So I'm going to brief summary of what I'm going to talk about. The first two things here, and maybe the motivation as well, I think we've probably covered, but I will go through them just to have a self-sufficient presentation. So firstly, this is very similar to Vitaly's slide, and it's just going to clarify that when we're considering our crystal sets here, we consider them as periodic point sets with the points being representing the atomic centers of the crystals. And we have a serious problem with ambiguity here, where any crystal structure in regards to a periodic point set could be represented in an infinite number of different ways. So here we just have the mathematical definition here that we're going to use moving on. And again, with the problem, we have a very one periodic point set here that can be represented with multiple unit cells, and even with a fixed unit cell, it can still have a completely different motif set of points assigned to it. Again, we're going to talk about crystals under isometry, and this is where we want to consider periodic point sets that differ by translation or rotation to be considered the same. We do have an inclusion of reflection here in terms of isometry, but most of the time we'll be working with rigid motion, although in this context, as you will see, that shouldn't affect things at all. And I just have a brief second example of a unit cell motif pair here that actually would be extremely difficult to realize was actually the same periodic point set. And it's only when you place it in its environment that it can become more clear that we're actually considering the same thing. So I'll briefly rush through this as well, because we talked about invariance all day. And this bridge length is, again, an invariant, but it's most important in the context of the ISO set, and the ISO set is complete. Now, this is fully complete. This is not generic completeness, so we do include all of those algebraically dependent definitions of point sets, and depending on your use case, this could be incredibly important. We don't want any kind of singularities or discontinuities. We're dealing with sort of representations of these crystal spaces. Yes, when we're working with individual point sets, we can just perturb them slightly and we can use things like PDDs or the other invariants that have been seen, but sometimes we actually want to move over those dependent point sets. And currently, the ISO set is the only proven fully complete invariant. And I will quickly introduce the bridge length before saying how it gets used in the ISO set calculation. So this is just a whole splurge of mathematical notation, but I will briefly explain it in English. When we have our periodic point set, in this case, we're using 2 points within a square unit cell. We could, when we look at the infinite space, again, we're on a plane here, of points, and we pick any 2 points, we need to be able to find a chain between them, and we want to minimize this distance. So what this distance is a jump between points, and we want to minimize the largest required jump to connect any 2 points. So there's a couple of other ways that we can describe this. One that works out quite nicely is sometimes described as increasing radius of the balls with the center of the points. And when they all touch each other into one cohesive mass, that's half of the bridge length. The version that I really like to use to describe this is if we consider all of these points as radio towers, the bridge length is the required signal strength that you transmit from these radio towers to be able to communicate to all radio towers.
That particular pattern is because you have chosen the origin of the unit cell where it is. If you were to move the origin of the unit cell, you would connect that up in a different ways. If I understand that.
Almost. So it would look different, but it would actually create the same graph regardless of unit cell. So this actually hints at a later concept where we have these vector labels to these edges. And those would change based on the origin of the unit cell or the orientation, rotation. However, the end result, the actual distance, will not change.
No.
So it doesn't matter how you look at
the invariant translation.
Yes. But yes, the starting unit cell does play a part in the calculation, but the end result is completely invariant of that. And yeah, I'll explain the little vector integer labels soon. So the original motivation is, if you recognize this image from Vitali's comment reference to the isosets, was, oh, 1 second. Actually, I will explain that. I've got a picture of the ISO tree afterwards, which again is similar. So I'm first going to just talk about these other motivations that come out outside of crystallography. So Janusz briefly mentioned VLSI. So in terms of the concept of constructing computer architecture uses repeating patterns, and it can be very helpful to have these values for communication. We also have some interesting things in terms of finite state machines, or more specifically, vector additive systems with states. They're all completely different areas that can use this concept, and I feel that it should be such a fundamental concept that is actually impossible to find in the current literature. I feel like this is a length, a radius that should be considered similarly to things like packing radius or covering radius. Except in this context, it's to do with connectedness. Now, the original motivation for why we were trying to calculate this bridge length is based in the isosets. And so Vitali introduced these alpha clusters. So these alpha clusters are balls of radius alpha around each point. And then we consider them, if they are rotationally equivalent to other balls around different points, we consider those points to be equivalent. And we split these balls into equivalence classes. At the very top, if the radius is 0, all points are identical, so there's only one class. But as we increase this radius, these classes split apart until eventually they split no longer. And we consider this point a stable radius. So only very briefly going into this, but the most important part is that when we are calculating the isoset, or we are calculating the metric between isosets, this radius has a huge effect on the actual calculation time. And if we would just look at the complexity of isoset calculation, it would just be cubic in the number of points. But that hides so many issues in terms of the radius. If the radius is too large, we are calculating that error, that difference, cubic in time over all of our calculations. So if we can reduce this, it's incredibly helpful. It turns out that across all point sets, the only thing we can be certain of currently is that this stable radius is at least 7 times this bridge length. So the amount that we can reduce our upper bound estimate of the bridge length has a huge effect on how efficiently we can calculate this invariant. And I say upper bound of bridge length because up until these calculations, this algorithm that I'm going to briefly describe, our upper bound of the bridge length was actually very high. There wasn't much in the literature to help us get a good result. And briefly talk about those differences right at the end with experimental results. So the first thing I'm going to quickly introduce is just a little bit of graph theory in terms of some discrete maths, which is the Kruskal's algorithm for minimum spanning trees. So in the finite case, this is a really simple thing to calculate. We want to find that minimum necessary jump again. And it's exactly the same as finding the longest edge length in a minimum spanning tree. And we have lots of lovely algorithms that have existed for a very long time to calculate this result. And it turns out that the algorithm in the periodic sense is pretty similar, but with some very noticeable differences. So quick run through of Kruskal's algorithm, we simply add edges in increasing order. And if we create a cycle with any of those edges, by adding any of those edges, then we do not add it. We can repeat until the whole point set is fully connected. Now, the problem is I used a lot of terms in there that just don't work in the infinite sense. So for example, consider all edges in increasing order of length, right? We're talking about suddenly an infinite number of edges. If an edge forms a cycle, disregard. Well, actually, that doesn't work either. When we're dealing with, actually, I'll cover that one a bit later, because I think that'll make more sense when I have the relevant diagrams up. And also, at the end here, I have stop at m-1 edges, m in this case being the number of points. We can't be certain of that either in the infinite case. So the first thing I'm going to say is, let's say we've got this finite algorithm. It's all lovely. We can use the minimum spanning tree. We can use Kruskal's algorithm. Surely all we need to do is take a finite subset of our infinite periodic set of points and just use Kruskal's algorithm on this. Now, hopefully you can see where some of the problems come in this. I've designed a nice little toy example here of a point set with just this lone point in the corner of the unit cell. Now, when we take a finite subset, in this case a supercell of unit cells, and just try and find the minimum spanning tree, we hit an error, we hit a problem. And that is that we're having to jump all the way to this lone point in the corner. But if you can imagine this in the infinite, we can always just go around. Yes, we want to connect from this point to this point, we can comfortably go around using much shorter edges. And we can always do this in an infinite crystal. So actually the bridge length should only be this value. But we can increase this style of point set arbitrarily. So in this case, we want to make sure, we've got a bridge length of 2, but we want to pretend that it's actually 3. We can make one for that, or for 4, or for 5, whatever arbitrary value that you want. And it just shows that it doesn't matter what kind of finite subset that you use in this case, we can construct a unit cell motif pair that messes it all up for you, unfortunately. So now I need to quickly talk about, about periodic graphs. So in this context, what we're actually wanting to create here is a periodic graph. And this is where I'm going to briefly talk about the Kruskal's problem. Kruskal's being, we don't add edges if they cause a cycle. But we want to create a periodic spanning graph in the infinite space. And unfortunately, those two things don't coincide with not creating cycles. If we have something that reaches all points, but we also want it to be periodic, in this case being whenever you perform any translation, it maps back onto itself, then we are forced to create cycles. There is no way around this. So we have to make some quite major modifications to Kruskal's algorithm to make sure that we're adding the right cycles. And what I'm also going to do is introduce the concepts of quotients. I think we've briefly talked about modular translations. I'll formalize this a little bit here in 2 dimensions, show you how this looks. So when we have a simple lattice, 1 point per unit cell, and we've connected the edges here. This we can consider in the closed form the quotient by translations here, which makes a lovely donut. In this case, it's somewhat simple to follow, but it quickly gets very difficult to follow. I'm also going to show one with two edges, 2 points, sorry. And what we're doing here is when we modulo by the translations, we get a closed form, which is exactly what we want. We love a closed and bounded for actual calculations. We can't use those computers on infinite space, unfortunately. And this is pointing to what Mike briefly said, is that when we have our different unit cells, we will actually change where these points are in our embedding onto the torus, but it won't actually change any of the edge lengths or the adjacency matrix of the graph here. And this is really important. Unfortunately, though, this is not just enough. We also have to label our edges, and then the unit cell choice rears its ugly head briefly. So what we really want is we want to be able to go from our point cell, our periodic graph, to our closed graph modulo translations, and then be able to go back again. Now, unfortunately, we could have our map from our quotient graph here, which don't worry, I barely introduced, so hopefully this doesn't come too far out of left field. We could map these back to a unit cell, but these edges on their own are just not enough. This goes from one point in a unit cell to the other point in the unit cell, but we don't know which. Like, as the yellow, blue, and green are all equivalent based on just those two vertices, how do we know that we want this yellow edge to actually go to the left or right here? And the way that we do that is by labeling these edges with integer vectors. And some other areas have names for this concept, called like gain graphs or voltage graphs. Yes, and there's elements to that which I will also introduce. So in this context, now that we have these labelings, we can actually pull this graph back to the infinite space. And you'll notice that just because I have a vector isn't enough, I also have to have a direction assigned to that vector. And these vectors are actually elements of a group, which is why some graph theorists call it gain graphs based on that. But voltage graphs is also a term that's used because we actually care about paths or cycles, and this is integral to how we use these graphs that are being built. And it leads, yes, it leads to our question of which cycles do we add and which do we not. So what we're currently doing is we start with, actually, I will just, yes, go to the actual full algorithm here. We're starting with an empty graph. So as you can see in this instance, and we consider all edges in increasing order of length, which is an infinite list. Now this is, I'm just going to say this. If I've got a little bit of time at the end, I can explain how we go about this process because it's not trivial. But in this context, let's just assume that we've got that list and we can just pick edges out of it. Now the problem is sometimes we will add these edges in here and we'll create a cycle. How do we know which cycles are important and which cycles aren't? We're going to use these translational vector labels. So the English description is if it forms a cycle, but it doesn't contribute to connectedness in the lifted graph, then we would disregard. So if you imagine that we're building this green and blue, but we haven't yet added the yellow edge, you can see that that connects all of the points in the kind of vertical direction. Now, if we wanted to connect this point here to this point, it wouldn't contribute to any connectedness in the lifted graph. So it would create a cycle, but it wouldn't be one that we want. Whereas if we're adding this yellow one, again, it creates a cycle with either the green or blue, but it benefits connectedness in the infinite space. And how do we ascertain whether or not that's happening? We can use these labels. So again, another hand wavy one that will be explained. When do we stop? We stop when the lifted graph reaches full connectedness. Again, not a trivial concept. So now I'll introduce the way in which we store the data of the translational vectors, which is in this translational matrix. And this is how we know when the full graph is connected, and also how we know if a cycle is important to be added. So each vector represents a cycle that's been added. So when we add one edge to this, let's say we start with the blue edge, we add that in, doesn't add to the translational matrix. But as soon as we add a cycle, we will add the cycle sum here of that. So in case this blue-green, here we add these two voltages together to get -1. And this -0, -1 cycle sum perfectly represents the movement from blue and green to 0, -1 integer vector in the lattice of unit cells. And when that happens, we potentially have improved the connectedness of the lifted graph. If that cycle sum ends up being 0, the 0 vector, it exactly means that we have formed a cycle in the lifted infinite graph. And so it's not a valuable edge. We do not want to add it. Now the question becomes, when I said taking a point here to its relevant equivalent, translationally equivalent point in another unit cell, after blue and green have been added, that doesn't benefit. That creates a cycle, but it doesn't benefit us. And why is that? It's because the cycle sum vector, this vector that was previously added, the new cycle sum is integer dependent on previous vectors in the translational matrix. Yeah. So what we do is basically, that's for the full connectedness. Where did we start?
34 minutes.
Okay. So we're keeping track of the sums of all of these cycles. And if we add a new edge, it creates a new cycle. If it is dependent on previous, an integer combination of previous cycles, what that actually means. So for example, we've already got these 3 edges and we want a cycle from here to here, or we want to add an edge here. Then what that would do is if we added it with any other edge, let's say blue, we would create a cycle. So it would go from here, over here, and then add a blue. So that would be the new edge, and then add a blue back, and it makes a cycle. Now, unfortunately, it's that integer vector can be made up of the cycle that is constituted of green, blue, and yellow all together, and then the new edge. So that integer dependence actually shows that we have already connected those 2 points in the infinite space, and adding a new edge wouldn't benefit us. It would result in connecting 2 points that are already connected, and so we can discard that. Now, so this is in the finite case, we can be happy with n minus 1 edges. We got 2 points, it takes 1 edge to connect them. But in the infinite case, we also have to add edges that will connect across all of the dimensions. So in this case, we would be in, say, R2. We need not just 1 edge, but we also need at least 2 edges to connect a cycle that connects us in the x direction, and also some cycle that connects us in the y direction. Now, n number of vectors isn't necessarily enough, and I have this as at least n edges here, because it turns out that you can construct point sets or graphs that require more than n edges to be connected. You end up with a finite number of disjoint graphs in the infinite space, and you require at least one more edge to connect those. Do I have the final algorithm here? Yeah. So this is the algorithm with a whole load of changes. So this is still skeletally the Kruskal's algorithm. However, we're going to make a couple of changes here. So if an edge doesn't form a cycle, then we add it. It improves connectedness in the quotient space, so it's going to improve connectedness in the lifted space. If it does form a cycle, then we need to find the sum of the vectors of the edges along this cycle. And I think that's worth actually mentioning is, where did we get these vectors from? In this first step, if we add it to the graph and that edge crosses between two different unit cells, then that is the vector that we're adding. So in, for example, this direction, we would add a 1, 0 vector in the direction. And the direction is arbitrary. You can pick whichever one. We just have to make sure that our vector is related to that direction. So we find this translational sum. If the translational sum is 0, so trivially linearly dependent to an empty matrix, if it's 0, it represents the fact that we have found a cycle in the infinite graph, which means there's no point adding the final edge because we can reach it by previously added edges. If, however, it's not 0, then it gets a little bit more complicated, and we want to say it's linearly independent to the cycle sums that we have previously added to the matrix. So if you want to imagine this more intuitively, you could argue that you're going along multiples of previous cycles. So in the context here, we wanted to add this edge. What we're doing is we're doing one multiple around the green-blue cycle, and then another multiple around, say, like yellow-green for this. We end up with, because we have to go back to the same point, we end up with a previous cycle, and that would represent that this edge creates a cycle that is constructed, is a sum of the two cycles made up here. And that is completely continues across many unit cells. If you had a large edge that you wanted to add, you can find a path, you can construct a path from the translational matrix with the requisite number of cycles, which lift to paths in the infinite space. So the question is it linearly independent to the cycle sums previously existing? If not, then we add it, and we'll also add that cycle sum, and that improves the connectedness again. And when we finish when that translational matrix of cycle sums spans fully Zn. And this is very crucial, actually, because if there are ways in which it can span Rn, but not Zn. So it can span the reals, but actually be still consisting of more than one disjoint. And I think, I don't think I will have time to explain the infinite length. I will quickly go through the experimental results. We've seen the T2 data set before, and these algorithms were run on the T2 data set as well. And here are a couple of results. So these are a few of different T2 polymorphs. And you can see that the running time varies considerably. But I think the important part to note here is that our previously best upper bounds for what the beta length, the bridge length are, have been reduced significantly. So this is the ratio between them. So for example, in here, we had a best current upper bound of the bridge length being over 23, and we reduced it to below 2. And that's a factor of over 12. Now, factor of over 12 doesn't sound too much, and 0.7 seconds is quite costly in these calculations. But when we are trying to construct the iso set, which is an extremely complicated invariant to construct, a difference, a factor of over 12 represents, in the radius, represents a factor of, what's 12 cubed? I should, a lot, yeah.
More than 1,000.
Now, this isn't actually the best example that we have. Hidden in the 5,000 plus simulated T2 crystals, there is actually a factor that's 24. So our previous best has been improved by a factor of over 24, and that cubes to over 15,500 difference. And what that represents in the actual real world calculation of the ISO set is, for example, if that crystal took an hour to calculate the ISO set, it would now take 0.2 seconds. And that's simply by finding this bridge length bottleneck, creating an algorithm that calculates it in a respectable time. Yes, this is costly in the world of millions of crystal data sets, but I think you can afford me a second or two of calculation if we can improve the complete invariant calculation by 15,000 times. How's time?
Yeah, that's it.
This is yes, this is my conclusion. It's that justifying the value of the bridge length through a 15,000 plus factor improvement in this only proven proven complete invariant, as I said.
Okay, thank you. Stop recording.